Hi, my name is Sunan. I'm a research assistant working in the Figueroa robotics lab at the University of Pennsylvania. Today I'm presenting my work with Haihui Gao, Tianyu Li, and Nadia Figueroa on Directionality-Aware Mixture Model, parallel sampling for efficient linear parameter varying dynamical system learning. So one key focus in our lab is to enhance human-robot collaboration, and the one really useful interaction between humans and robots is to teach robots new tasks from demonstration. And here is one example of kinesthetic teaching, where the human first guides the robot to perform a shelving task, and after demonstration, the robot can recreate the same task despite human disturbing it. So under the hood, this is a classic trajectory planning problem. And what traditionally people would do is generating a sequence of time-dependent waypoints for robots to track. However, in the context of human-robot collaboration, we notice time delays are actually quite common. And when the robot resumes from a human interruption, we actually want the robot to pick up from where it left off, instead of sprinting to the next time index waypoint. So this leads us to approaching this problem slightly differently. Instead, we model the nominal trajectory as a dynamical system, or a DS, where x is a kinematic state of the robot and x dot is its time derivative. So for example, x and x dot will be the position and the velocity of the n effector as in this video. So now the question is, what does this function f look like, and how can we learn it from demonstration? I'd like to first introduce the idea of linear parameter varying dynamical system, also known as LPV-DS. The use of LPV-DS in a learning from demonstration framework has been greatly shaped by the work done by Nadia Figueroa, Mohamed Kassanre, and Oud Bilal. And we already see the strengths of using LPV-DS from the previous video, where the robot exhibits strong perturbation response and the stability at the target. Moreover, on this 2D example here, we see LPV-DS vectorize the entire state space, and even the unmodeled regions are generalized with some meaningful behavior that leads to the target. In addition, LPV-DS requires minimal data, making it effective with both multiple trajectories or a single trajectory. So the learning of LPV-DS follows a two-step learning framework. We first look at the mixing function gamma k here. Gamma k is a state-dependent function, and its parameters can be estimated by fitting a statistical model to the trajectory. And the one most common choice is using Gaussian mixture model, or GMM. In this example here, we fit a mixture of two Gaussians to this trajectory, and depending on where our state x is, gamma k will distribute the normalized weight to the corresponding linear system. Now that we have gamma k, we can then estimate the parameter of linear system a sub k by minimizing the reference velocity and the estimated velocity. In addition, we enforce the following constraint here, which is the stability condition for LPV-DS using a quadratic Lyapunov function. And here in this example here, we see each linear system describe a distinct motion of the original demonstration. And the gamma k tells us which linear system is more dominant given where our current state x is. As you might notice, the performance of LPV-DS relies on accurate encoding of trajectory data. However, in this more complicated example here, we see GMM will model this entire bottom right region as a single Gaussian. And as a result, the simulation of running this LPV-DS will result in an error here. And while GMMs are really useful at clustering sparse points based on spatial proximity, they fail to produce physically meaningful results for trajectory data. And what's missing here is trajectory data have inherent directionality, while GMs do not explicitly model directionality. So to tackle this problem, we propose our approach, Directionality-Aware Mixture Model, also known as DAMM. So in this same example here, we see our model is capable of producing three distinct Gaussians in the bottom right region. And as a result, the reproduction is actually much more accurate and consistent with the original demonstration. In addition, we formulate our approach in a Bayesian non-parametric framework, where the number of Gaussians can be directly inferred from the data. In addition, we'll propose a hybrid MCMC, or Markov-Chain Monte Carlo method, that can achieve real-time or near real-time learning speed, depending on the amount of data we have. And the key idea of our approach is to incorporate directionality into the mixture model. And we do that by augmenting the state variable and Gaussian's parameter by one additional dimension. And I'm using the hat notation here to denote the augmented variables. To see how this works, we'll use this example here. And the goal is try to classify this point of interest between the two existing components. We first normalize the velocity at this point to get x direction, indicated by this black arrow here. And then we notice that direction vectors actually reside on a unit sphere, so we cannot simply subtract two directions to compute their difference. So the key operation here is a Riemannian logarithmic mapping. And by taking the norm of it, it will give us a measure of deviation in Euclidean space. So to see how this works, say we are comparing our point of interest between those two components. We notice that there's a large deviation between our x direction and the mu direction of the blue component. So if we do the mapping and take the norm of it, it will result in a large value in this additional dimension. On the other hand, our x hat is actually much lower when being compared to the red component. That's because their directions are much more similar. So due to this formulation, we notice that x hat is not a unique value, and it varies relative to the component it's being compared to. The augmented mean of each Gaussian is not appended with a value of 0. To see why it's 0 here, say our x direction happens to be the same as mu direction of the right component here. Or visually, the black and the red arrows are perfectly aligned. Then this log mapping will return a 0 vector on the tangent plane, and the norm of it will be exactly 0. The augmented covariance sigma hat is appended with a direction variance along its diagonal, which gives us a compact measure of how much directions vary in terms of magnitude within each component. So putting everything together, we see our point of interest is actually more likely to belong to the right component in this case. So how do we estimate the parameter of this mixture model, especially if we want the model to infer the number of Gaussians directly from the data? We notice that the posterior distribution of Gaussian mixture model is intractable, and it's very common to apply Markov chain Monte Carlo or MC-MC methods to approximate it. However, MC-MC methods are a class of iterative algorithm, so every iteration, we need to sequentially update each data point assignment and each Gaussian's parameter. That's why we propose a hybrid MC-MC method that combines the strengths of two different approaches to achieve significant speedup. Now every iteration, we can choose from either a split proposal or a merge proposal. And using the split proposal as an example here, say we are trying to split this right component. We first randomly assign those points into two new groups, which will be red and green here. We can then rearrange those points between those two groups by evaluating the conditional probability using Gibbs sampling. And then we notice that because those points can only choose between those two groups, we can actually evaluate the conditional probability in parallel. So we can update each data point assignment independently given the fixed Gaussian parameters. We can then evaluate the acceptance ratio to decide if we accept the proposal or not. And we notice that the split proposal can be used to create new components, and each Gaussian component is not a better representation of linear system. Here are a few examples of running our approach on hardware. In this first task, we want the robot to pick and place the object while navigating through the obstacles. And then we see our approach can nicely encode this trajectory while accounting for directionality. And when we run the robot with this LPV-DS, we see the robot can reproduce the same motion as the original demonstration. And our approach also fits in the incremental learning setting pretty well. Here, we want the robot to learn 3 different tasks sequentially in a single motion policy. And we see the robot can reproduce the latest new task while it's still able to preserve all the old ones here. We also see the application of our approach beyond LPV-DS. In this work developed by Tianyu and Nadia Figueroa, they introduced this framework called elastic transformation that is used to generalize the existing motion policy to new unseen tasks. And they do that by fitting a statistical model or a Gaussian mixture model to the trajectory. And then each Gaussian can then be treated as a link connected by joint. And by manipulating those joint angles, you can actually have the robot adapt to different behaviors. So the performance of this framework also relies on an accurate encoding of the trajectory data. So the use of our approach to produce consistent and physically meaningful Gaussian components actually fit in this learning framework really well. And the idea of working with direction vectors on a Riemannian manifold can also be generalized to the orientation in the quaternion space. So in this latest work, we further exploited this idea and developed an adaptive motion policy for orientation control. To summarize, we see the use of our work can improve the reproduction accuracy and the computational efficiency in LPV-DS framework, but we also see the potential it has in applications beyond LPV-DS in other domains as well. As the outlook for the future, we'd like to further explore the second-order DS learning to alleviate the stability versus accuracy dilemma.